Dear friends of power electronics, audience of this conference, ladies and gentlemen, good morning. First of all, I would like to thank the organizer of this conference for inviting me to present this keynote talk, and I apologize for not being able to attend the conference in person. It is, however, a great honor for me to be able to share my research here online with the conference audience. The topic of my talk today is inductance, which could be very familiar to many of you here, but at the same time, the concept of negative inductance could be totally unfamiliar to many of you. So in this talk, I'll explain the key concepts of negative reactance and how we achieve the synthesis of negative reactance. And hopefully the presentation will be interesting to you. Let me start with a bit of history. Inductance was introduced 200 years ago by an English scientist, Michael Faraday, who studied magnetic induction with a set of coils and identified the inductance property. Then, about a quarter of a century later, an American engineer, William Stanley Jr., developed a practical device that utilized mutual inductance, which was actually the modern transformer, and that became crucial to the power system development. Another person that is worth mentioning here is the Dutch circuit theorist, Professor Bernard Tellegen. Some of you may know him by his very famous Tellegen theorem, but actually he invented an important conceptual device known as the gyrator, which is like a transformer, but it interchanges voltage and current of primary and secondary sides. And his gyrator has a great impact to analog circuit development because it can be used to create negative impedance, like negative inductance and negative capacitance. We'll talk about it in the following few slides. So, what is negative inductance? In a nutshell, and conceptually, it is just a device that follows the same constitutive relation or definition of an inductor, that is, the voltage being proportional to the rate of change of current, or V equals L di dt, but the value of the inductance is negative. So what does that mean? Well, a negative inductance is like the opposite of an inductance, but it does not exist in the real world. And it should not be confused with the capacitor, although some people may mistake it as the capacitor can cancel an inductor. However, this is not the same. Capacitor and inductor together form a resonance tank, and hence the compensation design can be quite complicated as frequency precision comes into play when we try to design the cancellation or compensation circuit. So, as we said, there is no negative inductance in the real world, and we have to synthesize it. Now you may see, obviously, the negative inductance can cancel an inductance directly when they are put in series connection. That would make it far much easier to do compensation or cancellation of unwanted inductance, such as in reducing reactive current, and of course you can also imagine using it for control, as it can adjust inductance parameter values. And you may wonder how a negative inductance can be constructed, and I'll explain in this talk. We'll be using power converters to design a device that can mimic negative inductance, and the system also requires quite careful application of control so as to make the current and voltage comply with the expected constitutive relations. Talking about potential applications of negative inductance, the first thing that comes to mind will be the power system compensation. Instead of using capacitor banks, we can employ negative inductance. For the audience of this conference, we have inductive power transfer systems utilizing compensation methods for improving power capability and efficiency, and obviously negative inductance will provide a straightforward solution for cancelling or compensating leakage inductances. Finally, communication in the small signal sense, could actually benefit from the use of negative inductance. And recently we have seen very good progresses in metamaterials development that leads to implementation of high frequency small signal negative reactances. And again, these implementations are only suitable for small signal application and not for power system applications. Now, regarding the key challenges and limitations, first of all, let me reiterate that negative inductance is not available as a circuit element in the real world, and it is not stable inherently, and synthesizing it is not trivial. So at this point, I would like to emphasize that active implementation using gyrator has been achieved, but it is not meant for power application. It is only for small signal applications. Power circuit implementation has not been successful up to now. I'll come back to this point when we review the recent progresses later on. And finally, the cost is still very high. Even if we can design and fabricate it in active form, the high cost may present obstacle for adoption in applications. For small signal applications, the gyrator implementation has been well understood and applied. In the example here, we have a gyrator implementing a negative impedance converter, which converts a capacitor to negative capacitor. Likewise, a negative inductor can be designed using gyrator circuits. However, such implementation of negative inductance or capacitance is only suitable for small signal application. The closest application we can identify for power electronics applications is a paper published in 1997 by Funato, Kawamura, and Kamiyama, but their work was an indirect proof of existence. That means there was no actual negative inductance device produced per se, and the validation was based on a much bigger inductance, which appears to have a smaller value of inductance, and therefore the method indirectly produces an equivalent negative inductance. While this makes sense, we understand that standalone negative inductance has not yet been created. So up to now, we have only indirect proof of existence of negative inductance, and there has not yet been any successful implementation of standalone negative inductance. And in the following, I'll explain why this is the case. So let us go through the very basics of inductance. So here we have a standard inductance having the constitutive relation of voltage proportional to the rate of change of current. And in this particular case, we have the inductance being positive and the impedance increases linearly with frequency, and the input current lags the voltage by 90 degrees. Now for negative inductance, basically it follows the same constitutive relationship where the voltage is proportional to the rate of change of current, but now the inductance values here will be negative, and therefore the impedance will increase linearly with frequency. However, the input current leads the voltage by 90 degrees. Negative inductance does not exist in passive form because it is active, and it stores negative energy, or actually generates energy, as shown in this energy equation. It can be easily appreciated that circuits containing a negative inductance are not stable. For instance, here, if we impose a DC voltage, the current obviously will explode in positive time. And in the frequency domain, there is a right half plane pole. Comparing the negative inductance with the capacitor, we see very distinctive differences. The capacitor circuit is stable. Upon applying the same voltage, the current basically converges in positive time. And in the frequency domain, there is a left half plane pole instead of a right half plane pole. Now let me explain briefly how we design the negative inductance synthesizer. First of all, our application scenario is AC, and let's say it is a 50 Hz system. We're going to use a DC-DC converter to perform the power processing with the objective of forcing the current and the voltage to comply with a specific relationship, which is the negative inductance constitutive relation. And specifically, voltage has to lead current by 90 degrees, and the voltage should be proportional to the current with the impedance increases linearly with frequency. And now, because we need to ensure that the input of the DC-DC converter is always positive, then we will necessitate a high stack-up voltage to be connected in series with the input here. And this high voltage has to be generated by another DC-DC converter as shown in the diagram down here, and therefore we will require altogether 2 DC-DC converters as the minimum configuration. In addition, we need a DC power source for the purpose of power balance and any dissipation within the converters. In addition, a set of control circuitry will be needed and have to be very carefully designed to ensure compliance of the constitutive relationship for the negative inductance. In addition, as we mentioned before, sufficient DC voltage is required to maintain a positive input for the DC-DC converter. And finally, of course, maintaining power balance is important. In our lab, we have recently designed and fabricated such a system. Details of the whole system are omitted here as they are described in an invention disclosure which is being filed in the United States. Here we have typical waveforms of negative inductance where the voltage is lagging the current by 90 degrees. And if we double the frequency to 100 Hz, we see that the impedance doubled as well. And here's the measured waveforms of standalone negative inductance showing the voltage lagging the current by 90 degrees. We may also perform a very simple inductance cancellation test. And shown here, the top side is basically a series connection of a resistance and a normal inductance, and therefore you will see a typical phase angle difference between the voltage and the current. And at the bottom part of the circuit, we inserted a negative inductance, and our purpose is to cancel the original normal inductance. And the next page shows the voltage and current relationship in the case where the inductance has been cancelled by the negative inductance, and obviously the voltage and the current are now in phase. Now at this point, I believe we can readily envision some potential applications which are related to power system compensation, and of course the compensation problems associated with inductive power transfer systems. And hopefully with this new device, the conventional inductor capacitor resonance-based compensation practice can be fully eliminated. The same idea can actually be applied to capacitance. For normal capacitance, the impedance decreases linearly with frequency, and the input current leads the voltage by 90 degrees. For negative capacitance, however, the impedance decreases linearly with frequency, and the input current lags the voltage by 90 degrees. And again, negative capacitance does not exist in passive form, and negative capacitance circuits are not stable. We can also apply the same implementation for negative capacitance using the 2 DC-DC converter configuration. And here we basically follow the same design using 2 DC-DC converters, and we try to force the compliance of voltage and current relationship. For the control circuit, very similar to the implementation of the negative inductance. And here for the negative capacitance, we're trying to maintain the desired voltage and current relationship. And we also ensure that there is sufficient DC voltage to be supplied for the maintenance of positive input voltage for the DC-DC converter, and at the same time we maintain power balance. Here we have the typical waveforms of negative capacitance showing voltage actually leading the current by 90 degrees. And we also compared the two different frequencies, 50 Hz and 100 Hz. And we are able to confirm basically the change of the impedance magnitude when the frequency moved from 50 to 100 Hz. Again, we can perform very simple capacitance cancellation tests. And on the top here, we have a resistance connected to a capacitor, and we see a typical phase angle difference between the voltage and the current. And the bottom here, we actually have a negative capacitance canceling the original capacitance here. And we'll see basically the voltage and current being in phase. Finally, in the last two slides, I would like to discuss some potential benefits if the negative inductance is being applied to compensation. As summarized here, the first benefit is the reduced sensitivity to frequency variations. Negative inductance does not involve resonance-based compensation circuit, which is sensitive to frequency. By using negative inductance, we can perform direct cancellation of the inductance value. The second benefit is that there is no concern of over or under compensation. Specifically, negative inductance improves the efficiency of electrical devices by reducing power wastage in reactive currents without posing additional constraints in over or under compensation. And finally, precision design will be unnecessary. In fact, it's no longer crucial to have capacitor and inductor values to be designed precisely for self or mutual cancellation at specific frequency or a narrow range of frequency. In terms of future development, we foresee that as technology advances, the application can be further broadened. Now, we have to remember that we are now taking a completely different approach in cancelling reactances. And those issues arising from oscillations due to LC circuits and incomplete compensation could be fully eliminated. So at the beginning, we talked about compensation or cancelling or direct cancellation of inductances. But then as we move to the future, we anticipate enhanced power quality by using negative inductance, basically focusing on mitigating power quality issues such as voltage sags, flickers, and harmonics. And if negative inductance technology can be miniaturized and integrated into power systems, it could also lead to more compact and lightweight design for power electronics equipment. And as we move to the future and along the carbon neutrality path, it could potentially assist in managing fluctuations in power generation and help stabilize the power grid during renewable energy ramp up or ramp down periods. And all this obviously will require further research, and at this point we have demonstrated the possibility of designing negative inductance, and obviously we have a number of issues that need to be resolved before the technology can actually be deployed for practical applications. Finally, I would like to thank my former students and postdoc. The idea was first conceived 17 years ago, and the initial problem was power factor correction, in which the input resistance synthesis is the core requirement. And then we extended the idea to general impedance synthesis. And now, 17 years later, we continue to explore negative impedance. And at this point, I would like to thank in particular Dr. Ding Li, my postdoc, in designing the feedback control circuits and performing the experimental measurement. This concludes my talk, and I hope you find the presentation interesting. Thank you so much again. Thank you.